In this video, I'm going to motivate hypothesis testing. So here's an example with website load times. So suppose that I say the average load time for my website, www.stat50.edu, is under 1 second. And you say, okay, let's verify that. So you collect a sample of 100 page load times. You get a sample of actual data, and suppose that the standard deviation is 1 in your sample, just to make things simple. If you see x bar equals 0.5, then you don't really have any reason to doubt my claim. However, if that you saw x bar is equal to something large, like say x bar was 15 seconds, then my claim looks really unrealistic. Because 15 is really far from 1. And I said it was 1 second or less, but you got an average load time of 15 seconds. That means it could still be 1 second, but then observing a mean of 15 is really unlikely. So we can make this statement more precise using the central limit theorem. So the central limit theorem says that x bar, it gives the distribution for x bar. It's normal with mean mu and sigma squared over n. So in this case, we suppose that mu is equal to 1. Suppose then that the mean is 1, and the x bar, the value that you actually observed, is 1.2. Now it's not so clear whether the claim is true or not. Like, is this value very unrealistic or not? So let's find out. Let's calculate it. And the way we can calculate it, we can calculate the probability of seeing a value of x bar that is at least as extreme as 1.2 here. Because we know that if mu is equal to 1, and we have sigma squared over n is equal to 1 over 100, then x bar should be distributed as normal with mean 1, variance 1 over 100. So we can calculate this probability. So here's our probability density function for x bar. It's our standard, not standard, it is the normal curve that we've seen many times, the probability density function for x bar. We want to calculate the probability. So this is where we suppose the true mean is 1, but the value that we actually got in the data is 1.2. So what's the probability of getting something that extreme? So to answer that question, we need to look at this area here, this area on the right-hand side. So the solution to this probability that we're interested in here, the probability of seeing something at least as extreme, that is just the area to the right of 1.2. That shows us the probability of getting something as extreme or more extreme than 1.2 because it seems far from 1. So we can calculate this. We know the parameters for the normal distributions. We can find out what this area is. And here is the R code to do that. In R, it has, so we're looking at a p-norm of 1.2 rather, with a mean of 1 and a standard deviation of 0.1. And the reason the standard deviation is 0.1, it is the square root of the variance here. So the square root of 1 over 100 is 1 over 10, which is 0.1. So here is our calculation. And then this is equal to 0.02275. Okay, so that is the probability of seeing something as extreme as this. So roughly 2% or so. So this sort of thing happens, right? But suppose instead of it being 1.2, suppose x bar was equal to, say, 1.5, okay? Then it's the same sort of, the exact same calculation here, except the probability that we're looking at is now, instead of 1.2, it's 1.5. So we replace this with a 5, see what we get. So this R spits out a number that looks like this. It's 2.8665. I'll write exactly what R shows. 16E negative 0.7. You might see this and think that the answer is 2.86. No. That's not what it is. That's not what you should look at. Look at this E negative 7, okay? So that's the thing that matters. And so what this number is equal to, this is... So this is shorthand notation for writing 2.866516 times 10 to the negative 7. Okay, so this E is for exponent, and that's 10 to the negative 7. So what it means that we really have is 0.00000286516. So this is what the actual answer is. Very small. Very close to 0. Which means if we saw a value of 1.5, then the original claim that then if it's actually equal to 1, if 1 is really the center of this distribution, then seeing a value of 1.5 seems totally unlikely. We shouldn't be seeing things that extreme. Therefore, we would have to conclude that the average load time, when I said it's under 1 second, we would have to say, no, it's not. It's not under 1 second. It's larger than that if we see a value of 1.5. And that's how we make it precise. So if we plug in, for example, x bar equals 15, we'll get something over here that's very much closer to 0. It's not exactly 0, but it's much closer to 0. Okay, so this is the general idea of hypothesis testing.